Hello and welcome to the Computer Vision Festival, hosted by the AI Accelerator Institute, a global community of over 400,000 AI leaders and practitioners, all striving towards one shared goal: inspiring the next generation of machine intelligence. With expert presentations on the festival agenda covering everything from space exploration on Mars to self-supervised learning, you're in for a treat. If you have any questions for our speakers or want to connect with them further, then ask away in the comments sections of the video and hear them answered at the end of each session in our live Q&As. If throughout the day you're loving the content, then be sure to check out the AI membership plans, where you can get access to exclusive content in the form of interviews, reports and articles. Access all areas passes to all past and future events. You can also join our Slack community, which is home to more than 2,500 fellow AI, machine learning and computer vision professionals, and is full of dynamic conversations and contributions. So if you're not already a member, come and join us today. Sign up using the link on the AI Accelerator Institute website. I want to say a massive thank you to all of our sponsors and partners for helping us to bring the festival to your screens today. Our amazing speakers for contributing some awesome content, and to you, our attendees, for joining us today. That's it from us, so go ahead, sit back, relax, and enjoy the festival.
Hi, I'm Steve Chen of the Jet Propulsion Laboratory, and I'm very excited to be here at the Computer Vision Festival to talk to you about some of the incredible work that's going on at the Jet Propulsion Laboratory in computer vision, machine learning, and artificial intelligence for space exploration and science. So first, JPL has a long history in using computer vision and machine learning for dealing with immense data streams and immense data sets. Going all the way back to 1993 in the Palomar Digital Sky Survey, this was about 3 terabytes of the northern sky data, which is about 5 times 10 to the 7th galaxies and 5 times 10 to the 8th stars. And this data previously, when it's acquired, it's just acquired, typically even in a non-digital format. And then astronomers had to manually go and assess it to figure out how many stars, what are artifacts, what are galaxies. And some revolutionary work was done by Usama Fayyad, Nick Weir, and all in the system called SkyCat, which used rule-based learning, similar to what's now called random decision forests. And they actually cataloged this entire data set into sky objects, and they also used the technique of transfer learning for classifying faint objects. So humans would manually label the subset of the data that was digitally captured, and the machine learning used the analog data, which is a larger data set, to classify based on just those features. And so this enabled them to actually classify several orders of magnitude fainter objects. And this kind of work is continuing on till today. Recently, the Intermediate Palomar Transient Factor, and even more recently, the Zwicky Transient Factor, are using machine learning to automatically triage and detect visual transient events. And these would be things like streaking objects or supernova. They have aspects of continuous quality control and retraining. And what this does is this actually takes on the order of 10 to the third objects or artifacts that are seen every night in the data set and triages them down to about 50 that are then suitable for human review. And this is great work by Uma Rabapragada and her team. This work in computer vision doesn't just apply to the visual domain, but actually applies to the radio astronomy domain. And here, machine learning is used to automatically triage radio transient events that are correlated across multiple radio telescopes all around the world. And one of the greatest achievements here is the Very Long Baseline Array Fast Transients Experiment, or called VFASTER. Again, they use random decision forests and computer vision techniques and continuous quality control and retraining. And this is work by Kiri Wagstaff and her team. So machine learning and computer vision have a long history of work, a long history and heritage at JPL and NASA in dealing with very large data sets. These kinds of techniques are also used to automatically classify data for images acquired by the Mars Science Laboratory rover. This has been on Mars for about 10 years. And it automatically triages data into different categories for what's called MSLNet. And this is for engineering purposes. It figures out what are drill holes, wheels, mass cam calibration targets, and also remote sensed imagery from the Mars Reconnaissance Orbiter, which is one of the highest resolution orbiters, highest resolution cameras orbiting Mars. They have trained machine learning to index images there to classify different things like craters, dark slope streaks, Swiss cheese, and bright sand dunes, as we can see in the upper right, for what's called HiRISE-Net. Again, this is work by my colleague Kerry Wagstaff. But one of the things that we're very excited about is actually what we call moving the analysis to the edge. And what that means is putting it on board the platforms that are acquiring the data, and that's important because then they can make decisions based on what they understand that they see. So in 2003, we actually put such kinds of classification software on board a spacecraft called Earth Observing 1. Earth Observing 1, as it's obvious from its name, looks at the Earth and sees different kinds of science phenomena. And so what we did is we used support vector machine learning techniques to automatically interpret images, to look at clouds, look at snow, water, ice, and land. And this allows us to track the growth and retreat and the freezing and thawing of the natural world. And this is useful for things like determining ice breakup or measuring glacier sizes. We also have used Bayesian thresholding techniques in order to automatically discriminate between clouds and non-clouds. This is used because typically in the middle latitudes, about 2/3 of each image is cloudy, and a lot of times that's not what the scientists want, so you can compress the heck out of that part of the imagery. This is again cloud detection using a system called TextureCam, which uses random decision forests. This is from the IPEX CubeSat. And the most powerful image processing that we've done on board is what we call onboard hyperspectral analysis. Here we're doing superpixel segmentation, so we're taking areas that are similar and blending them into larger pixels to increase our signal to noise ratio. And then we're using a technique called sequential maximum angle convex cone end member extraction. What does that mean? That's a mouthful. So our eyes see the world in three spectra, roughly speaking, red, green, and blue. We can build these instruments that can see the world in 50 or 100 or even hundreds of spectra. And what that means is for each pixel, they actually read out 100 values, let's say, and that gives us a curve, which is the equivalent of the color, but it's a 100-dimensional space. And because we can see these very subtle spectral differences between these objects, we can tell the difference between different substances we're looking at, and even subpixel looking at, that's a combination of this substance, this substance, and this substance. And at right, that's exactly what this shows. This is work by David Thompson. And those squiggly lines in the different colors, the green, red, blue, and purple, those squiggly lines actually, by the shape of those curves and where the peaks and valleys are, we can tell that that signal relates to calcite, muscovite, or alunite. And this is actually some work where we showed that we could do the same analysis on board or replicate some of the analysis on board as the legendary on-the-ground manual analysis done by Cruz and Grant. So this is the kind of very powerful reasoning we'd like to do on board the platform and move the smarts closer to the edge. This is another example from airborne data of Brian Bowie, Andrew Thorpe, Riley Duran, and David Thompson again. And here they're using deep learning techniques in order to find methane sources, spurious methane sources. And so they can fly an airplane over and take one of these fantastic imaging spectroscopy cameras or instruments and detect, very faint methane plumes that are from point source emitters, typically from an oil well that's leaking or something like that. And oftentimes we can compare and combine multiple kinds of data in order to get what we want. So this is actually some data taken by the WorldView 2 satellite of the Eyjafjallajökull eruption, which was in Iceland, a very major eruption of a volcano. And here we've used a random decision forest classifier, the TextureCam classifier we saw before, at right, and it's showing that it can tell the difference between plume and shadow and land. And then we take that plume, shadow, and land and geometric information that we know about the position of the sun, the topography, the digital elevation map, and the position of the spacecraft, and we can compute a bound on the height of the volcanic ash plume. And this is very, very interesting to the scientists because the scientists want to know the ash, what's called the plume injection height. That's a very good indication of how vigorously the volcano is erupting. So what we've done is we've gone from data, i.e. pictures of the volcano, to knowledge, how vigorously the volcano is erupting. Now, I want to make a shout out, and I'll come back to this subject later, for unsupervised learning. A lot of people talked about supervised machine learning. Unsupervised learning is very interesting. This is actually showing visual salience, and so it's picking out things that differ from the background signal. In this case, it's a set of minerals on the top of volcanoes in Chile, but we could also give it different other features like texture and so on. Now I'm going to change topics a little bit and talk about use of computer vision and machine learning on Mars. As you know, we were very excited to land a new rover on Mars, the Perseverance rover, in February of this year. But active rovers and previous rovers have been very aggressively using machine learning and computer vision on Mars itself. And first of all, for the Mars exploration rovers, in 2007, we had automated processing to actually detect and track dust devils. So dust devils are very interesting because their atmospheric activity on Mars, and they can be as large as kilometers in height, but they don't happen all that often, so you don't want to take a lot of images hoping that you'll see them. So instead, what we wanted to do is develop a technique to automatically detect and track dust devils. And that's in fact what we did. So the red boxes at the top show the detections, and we do this by simple motion tracking and temporal differencing across a series of 20 images. And then we actually produce summary images that extract out the size of dust devils, because the scientists are interested in how often these happen and how strong they are. And that's a proxy, that's a proxy of that is the size and velocity and the strength of the dust devil, in other words, how opaque it is. And so what we actually produce is the bottom science product, which is the cropped out series of images with the dust devils extracted from them. And the rest of the image we gray out, and then naturally the image processing compression, the image compression techniques can compress the uniform gray quite well. When we did this, we also developed a technique to automatically analyze the clouds. It turns out the scientists are very interested in when and what type of clouds form. And what we do here is we in fact detect the clouds, and we can downlink summary products on this that tell us that are enough so that the scientists on the ground can tell what types of clouds they are and why they likely formed. And then we do this by finding the sky, which is the very homogeneous region, and then looking for variations within that. Eventually, someday, we would like to have these techniques for dust devils and clouds, in fact, enable us to just downlink the statistics on when the dust devils occurred and how strong they were, and when the clouds occurred and what type they were and how strong they were and their altitude, because that's in fact the important information that the scientists want. Now, even more interesting is autonomous targeting using computer vision. So there's a system that was in use on the MER rovers, in use on the MSL rovers, and will be in use for the Perseverance rover. And this is a system called Aegis. And its primary application, its most stunning application, has been on the Mars Science Laboratory Curiosity rover. And what it does is it finds targets for the ChemChem laser. The ChemChem laser is what's called a laser-induced breakdown spectrometer. And if we look at all these images of Mars, what's common about them? They're all covered with this rust-colored dust. So if we went and measured that all over Mars, we wouldn't be very happy, because they'd say iron oxide dust, iron oxide dust, iron oxide dust. So the scientists and engineers are very clever. They developed this laser-induced breakdown spectrometer. What it does is it fires a laser that burns off the outer coating of the rock that's been weathered with this dust, and allows you to measure underneath that dust and determine what the underlying rock is. The problem is it's a very small laser, and it takes a significant amount of energy and work to fire it. So what used to happen is the scientists used to take an image of a region, download that image to the ground, figure out where the targets were in that image, figure out where they wanted to target the laser, and then figure out the commands to target the laser there, where to point it, and very important, make sure you're not hitting the rover when you fire the laser. And then they would upload those commands, and the next day they would then fire the laser and get their data. Now what we have is an automatic system that basically does a lot of computer vision things in order to automate that process. It takes this NavCam panorama, it actually extracts the candidate rocks. The scientists give a set of science criteria that they'd like to choose by, such as the intensity, the size, the shape, the distance from the rover, and then they can specify how to filter the targets based on these criteria. They can say, hit up to 3 targets that are greater than this threshold, or hit the highest value target. And then from that, the image processing software automatically determines the center of the target, as well as the distance to the target using stereo. And then it actually acquires what's called a ChemCam LIBS raster. The size and direction of that raster is pre-specified as part of the overall stuff from the ground. So they can say, do the raster across or do it vertically or so on. And because of this, it's a tremendous boon to the science on the rover. This is fantastic work done by Tara Eslin and Raymond Francis. Those are the different citations if you have more interest. And there's follow-on work to this. There's a version for the SuperCam instrument on the Mars 2020 Perseverance rover. And in the future, they'd like to use machine learning to automatically classify what are called contact layers, the different regions. In this case, we can see in this image, there's conglomerate, mudstone, and then an alteration or vein. There's picking out these different chromite and little dots. We would like the system to be smart enough to actually label those different regions and then be able to make its science decisions on where to target and maybe place robotic instruments based on those kinds of criteria. Another example of dynamic targeting that we'd like to do is the SMICE's ice hunting radar. And basically, this is a mission concept. This is not yet accepted as a mission, where we would have a spacecraft flying over the Earth, and we actually used machine learning to learn a classifier for deep convective ice storms. And what we do here is, as the spacecraft is flying over the Earth, it looks ahead with this radiometer instrument and tries to find these deep convective ice storms, which are the darker colors here, the darkest red. And as it does that, it has a radar that it can turn on and target these deep convective ice storms. And it takes a lot of energy to take these measurements, just like the ChemCam laser, with this radar. So what we're doing is we're saving the radar for the most important science targets, which are detected by the radiometer, and we're hunting these ice storms. So this allows the mission to be much more energy efficient and much more targeting efficient, and therefore get better science and better bang for the buck. And this kind of smart targeting using computer vision is not just on Earth and on Mars. We worked on this fantastic European Space Agency mission called Rosetta, which some of you might have seen, where we studied the comet Churyumov-Gerasimenko. And what we had to do there is we had to plan out these activities weeks or months in advance. And so we wouldn't know if the comet was going to be outgassing, just like the dust devils on Mars, and sending out these plumes. What we'd like to do is we have this narrow field of view instrument called MIRO, which tells us about, it's a microwave instrument that tells about the composition of the gas in the plume. But since we don't know exactly where the comet is going to be and where the plume is going to be weeks in advance, we just did these broad sweeps across the whole area. And so what that means is we get a lot of data, but we don't have a very good temporal evolution of the data because these sweeps take a while. What we'd like to do is do a targeted sweep across one of these plumes as we track it through its evolution as it rotates into the sun and the plume forms and then the plume goes away. So we developed machine learning techniques that do exactly this. This is a sequence of about 12 hours of data. Each frame is about 20 minutes apart. And as you can see, those lines are computer vision tracking of the plumes using a range of edge extraction and thresholding techniques. And this demonstrates this capability that if we could fly this on the next mission to a comet, we could track the plumes and take those targeted measurements that I'm talking about. And then finally, one of the things that I want to say is I've talked about single spacecraft, but in fact, we've been linking together multiple spacecraft to track different science phenomenology at Earth. And why Earth? Well, because we care more about Earth than other planets, and also because we have more satellites to link together. So one satellite can detect, let's say a volcanic eruption and tell another satellite, hey, here's something you should take a look at, and then that other satellite will, take observations, and ground stations could detect, a volcanic eruption. In the lower left, those are seismographic and tilt meters that and infrared cameras that might detect an eruption, and then we would stream that data and use it to task a satellite. And this has been tremendously effective at volcano monitoring. In over a decade of operating our monitoring system, over a third of the scenes that we acquired then were active volcanic eruptions. We've also used it to track flooding, wildfires, cryosphere, and oceanographic events. And so now I'm just going to go a little bit out there and talk about how talk about a topic that's near and dear to my heart, which is how we really need advanced AI and computer vision and things like that in order to search for extraterrestrial life. Let's go way back. A few hundred years back, two explorers, Lewis and Clark, went to the Pacific Northwest, and they explored for 2 years. It took them 2 years to go from the Mississippi River to the Pacific Ocean. And along the way, we think that we don't get to take a lot of data, from our space missions. They could only bring back about 80 pages of handwritten notes and sketches. Compare that with our space missions, where pretty much what we do is we walk 2 steps, take a picture, walk 2 steps, take another picture. Now, maybe your children or teenagers, they might do things like that with their cell phone. It may seem like that sometimes, but certainly, we have much more capability with our cell phones now than we had to capture this kind of data. And if we send a mission to one of the outer planets, let's say one of the moons of Saturn, or far more interesting, another star, we're going to have to be very efficient in the data we bring back because we're sending it from billions and billions of miles away, and so it's very hard to send that data. So we've been looking at machine learning techniques that would in fact enable us to do that, and this is now getting back to the unsupervised learning that I talked about. So consider the following experiment. When a summer intern was flying across the country, we had them take hundreds of images out of the side of the airplane. And what we do is we take those images and we cluster them according to certain visual features: color, albedo, texture, intensity variation, histogram intensity variations, and then we try and learn those clusters using unsupervised learning. And it turns out, if you have the right features, you get clusters. You get clusters like clouds, oceans, plains, mountains. You actually get this very interesting cluster of, a jet engine in the side of the image, because that's quite a distinctive feature. And what exactly we want to do is take those clusters and then return the map, just like Lewis and Clark, where they have the mountains, rivers, and lakes. But with our different features, we're going to say mountains, clouds, jet engine, and then send down examples of those classes that we see as the key to our map. And that's a tremendously efficient way to describe things. And most importantly, you don't get a distribution of images relating to, how often something was seen. So if you cross these vast plains, anybody who's driven across the United States in a car, it's pretty boring, after you see 5 or 10 images of the Great Plains. That's probably enough. You really don't need thousands of them, even though that might be a significant proportion of, let's say, the Midwest. So you can now send down n images per inferred class, and that's a much more interesting way to get down a data set. And so with that, I'm going to end my talk and enter into a discussion phase. And this is for people who would like to find out more about some of the AI, machine learning, and computer vision work going on at JPL. And I'm going to leave with the JPL mantra, which is, of course, "Dare mighty things." Thank you very much.
Hey, thank you, Steve. Hey, everyone, this is Ashok Ramani. That was a wonderful presentation and talk. Thank you for providing us with an out-of-world experience and walking us back in time with Lewis and Clark. I think we got quite a few of our attendees here from all over the world, and there's some really exciting questions here, and we'll try to answer some of them in the Q&A. But let's maybe start with a few things, Steve, and then again, let's make this conversational more of a fireside chat kind of thing. We don't have a fire here. We're all up early in California at this time, and we are holed in our own rooms. But anyway, let's start with the first one, Steve. Of course, you've seen quite a bit of AI use cases, ML use cases at scale, computer vision, right? Maybe let's start with the high-level question, right? What do you see as the biggest challenges in deploying computer vision and ML at scale?
That's a great question, and it's hard to know where to start because we have a lot of challenges. At NASA, the biggest challenge that we have is we have very complex operational flows. So if we take the Mars rover surface operations, we have long-term planning, which is in multiple weeks at scale. We have what's called look-ahead planning, which is several Martian days ahead. And then we have the tactical timeline, which is for literally the next Martian day. And we need to apply AI and machine learning within that process. Otherwise, it has no hope of being adopted. And so it has a different role at the different places in that process. And so the tactical timeline person is very concerned with the products they have to deliver and assessments of reliability. At the strategic level, they're willing to accept maybe a less rigorous product that just gives them an idea. When I drive to that region, it's going to be harder to drive, so it's going to take longer to drive. But the tactical person is obsessed with, can I drive to that spot right there? Is that safe? How tilted is the rover going to get when it drives there? And so one thing that's extremely important is how you get what is the operational process that you're trying to embed the AI, the machine learning, the computer vision into, because you want to give the user what they want. Another great example is I talked about the image processing for analyzing the volcanoes. More typically, before we came along, the data is organized by data set. So if there's an eruption in Iceland, you go to one satellite and you get their data. You go to another satellite, you get their data. You go to another satellite, you get the data. And that's very tedious for the users. And what the users actually want is they want it organized by episode. They want this eruption, all of the satellite data. And they just don't want the imagery, like I said in my example. They want the knowledge. So what we try and do is automatically process all of that data into the scientific quantities they want. I gave an example of plume injection height, which is the velocity that the volcanic ash is coming out of the volcano with. That's what the scientists want, or they want to know the magnitude of the thermal emission, which is actually quite mind-boggling. It's measured typically in gigajoules. That's how much energy is being released by these volcanoes. So they want the science numbers. They don't want the raw imagery. So that's an example of understanding the operational flow and the use case.
Got it. Cool.
So really,
thank you.
To summarize, it's like give the users what they want when they want it, which sounds kind of obvious, but as technologists, we usually don't do that.
Yeah, exciting. Yeah, there's a related question from Jinal Shah here, right, which is around how are AI systems built in for again space exploration, planets and moon, right? It's kind of an extension of what does it take to move these computer vision and ML models to the edge itself, right? And you talked a little bit about being more efficient about bringing back the data, right? So maybe can you highlight some of that?
Sure. So as in my Lewis and Clark example, instruments can produce gigabytes of data per second, especially a hyperspectral instrument or a radar instrument. And we typically can't bring all of that data back. So what we want to do is we're in the knowledge business, not the data business. And that's something that's true across, most of the people in this community. And so you want to find the most important data and both acquire the most important data, which is, when I talked about autonomous targeting and things like that, and then bring that back. The challenge is the spaceborne computing, as Ryan had indicated in the chat earlier, is lagging. So a typical processor that we would fly right now, the Mars Perseverance rover, has 2 Rad 750s. Actually, I think it has 3 because there are 2 in the RCE. But the way to think about that is that's a very old Mac Macintosh computer, like from the 90s. So those of you who are old enough to remember the colored computers, the blue one, the orange one, that's the processor there. It's a PowerPC architecture. But we're moving ahead to try and fly more current computing. The problem is the radiation and thermal environment that we have in space is very challenging. It gets very hot, it gets very cold, we have radiation hits, and that can cause both latch-ups and single event upsets. Right now on Mars, the Ingenuity helicopter and its base station on Perseverance has two Qualcomm Snapdragon 820s on it. Now that's about several years old cell phone technology. We have another experiment that is going on literally right now on the ISS, and there we have two Qualcomm Snapdragon 855s, which, for those of you who have a Samsung Galaxy S9, I think it is, that's the processor there. We have two Intel Movidius chips, which is very exciting. Those are flying actually on ESA's PhiSat right now. And we have NVIDIA T4 GPUs there as well. So we're experimenting with more powerful processing. I can tell you that as a software person, the number one bottleneck we have is the processors typically fly some kind of real-time operating system and not, let's say, a generic Linux, Red Hat Enterprise or Debian would make things a lot easier. And then we also need large amounts of RAM. 64 gigabytes of RAM would be fantastic. What's more typical in a spaceflight processor is, believe it or not, 16 or 32 megabytes. So,
awesome. And I think in some ways, Steve, you already answered Rushiraj's question on computational requirements for the edge, right? So that's awesome. There's another one here from Wendy Slattery, right? Let me see. Okay, are there any particular models that tend to dominate in the field, or are engineers spending most of their time creating newer edge models, right? You talked a little bit about transfer learning. Maybe you can highlight a few things around that.
Yeah, so the machine learning modeling is quite an interesting topic. So, as everybody on this chat probably knows, all the rage in the last 5 years is deep learning. But within NASA, we have to understand very much, what are the models being created, because it's typically a collaborative process between the scientists and the machine learning researchers or the computer vision researchers. All of the projects that I mentioned were many-year-long collaborations between science teams and, AI folk. So one of the challenges of deep learning is trying to understand exactly what it means, what the model means, is quite challenging. And a lot of our data is multimodal. It's not just literally one image that's interpreted in isolation. And so there's a lot of great work on which pixels are really triggering particular activations. But in terms of a deeper understanding of what a convolutional neural network really means, that's still eluding us. So one of the challenges is what is the physical model that relates to a data model or a machine learning model? And I joke a lot with my machine learning friends that machine learning is mostly knowledge free. That's not literally true. People, when they select the features and pre-processing, a lot of thought goes into that. But in some sense, the machine learning is completely oblivious to that. And so I always joke with them that machine learning is what you do when you don't know anything or when you're ignorant, because you just have a pile of data and you're kind of floundering around. And machine learning can do amazing things with that. But clearly the future is, we have model-based AI, which I spent most of my time in on command and control systems and scheduling systems. Then we have data-based AI, which is more machine learning. Obviously, we need both. And the questions are, how do you use these two together? And I would say that is the tremendous challenge that we have right now. I mean, we have this great revolution in computer science that has now made all this data machine readable, which really has allowed this data science and machine learning revolution. Now we need to make knowledge machine readable, which is something that has eluded AI researchers. I'm quite old, so it's eluded AI researchers for decades, let's just say. So that's, awesome. To me, that's the future challenge.
Awesome. Model-centric and data-centric AI. Maybe a little bit pivot on the data side, right, Steve? So one question here was around public data sets that NASA has. Maybe can you touch upon some of these data sets available for folks to play with and build their research on? There was one question around that I thought I saw early on in the talk.
Yeah, so absolutely. Almost all of the NASA data and almost all of the space data is publicly available. So that's the good news. So like NASA, the Earth science data sets are available at what's called the DAC at Goddard Space Flight Center. And the deep space data sets are available at the Planetary Data System, which has a lot of JPL people working on it. And then if you're interested in Earth science data, the European Space Agency's Sentinel series of missions produces fantastic, unbelievably fantastic data that we actually use quite commonly. The challenge that I'm going to warn people about is that's data and not knowledge. And so it takes people years, even decades, to understand that data and understand how to use it correctly, how it's calibrated, and what the questions are that you would want to answer with machine learning. So I would encourage people to partner, just as we always do, to partner with science teams that have years to decades of experience in working with this data. And so like computer vision and machine learning people can partner with the scientist, and that is the true win, the synergy. And we would not really, we have lots of experience with this, and we would not really imagine what we jokingly say, go in not armed with an expert. So like we work with volcanologists. There are volcanologists that we've worked with for decades. There are hydrologists, cryosphere scientists, planetary geologists we work with for literally decades. And that's what I would recommend.
Awesome. There's a few more questions, but there's one very important topic, Steve, that I thought we can discuss here, right? Is there's an emerging discipline and there's a lot of discussion around responsible AI, right? And bias in ML, right? So how do you deal with JPL and NASA with bias, right?
That's a fantastic question. So we absolutely are very concerned with that topic, but we're concerned with it more in a scientific case. So usually people are worried about, a societal and ethics case, that machine learning is going to learn some algorithm that discriminates in hiring, discriminates in giving loans, or even discriminates in, fraud detection. So that we have exactly the same technical problem, but it's kind of in a different application sphere. So I talked about the Aegis autonomous targeting. So what happens if Aegis autonomous targeting picks out a particular kind of rock more easily, which I'm sure it does, because it's using particular computer vision techniques to find the edges and the targets. So, I'm sure particular shapes of rocks are more easily detected. So since we're now using that system to select our targets, our data is now biased towards targets that have, a stronger albedo differential from the background, or maybe if it can pull out targets closer to the rover easier, then we're going to get targets that are in less rough terrain because we tend not to drive the rover into rough terrain. So those targets are going to be closer. So we are also obsessed with understanding and characterizing the bias of our AI systems that we use in space, although the stakes are a little different. If we don't characterize the bias correctly, then we're going to end up with bad science. And that's the whole purpose of these missions is science. So that's a big issue. So we have groups that work on characterizing the bias of these systems. We actually work a lot with the scientists on trying to model the bias. And that's actually a fascinating data science meta problem in itself. How are you constructing models of the bias of your AI/ML system?
Awesome. Cool. I'm just going to look at if there's any more questions here. There's a couple here. Maybe we can take them before the end of this session. Aniket Prabhu has a question around reinforcement learning, right? You talked a lot about bringing back automated triage and efficient data back, right? But are there any cases of reinforcement learning, online learning?
That's a fantastic question. So we wish there were applications of online learning. So the space community is very risk averse. And so right now, all of the machine learning applications that I talked about are offline. And I would say they're offline on steroids in the sense that there was a very careful analysis done by a very concerned science team and a very concerned set of machine learning researchers to show that the machine learning was performing very well. And particularly, the greatest examples of this are the extremely large data sets that I talked about. So the Mount Palomar Sky Survey, more recently, the Intermediate Palomar Transient Factory, the Zwicky Transient Factory. The Zwicky Transient Factory data is very interesting because that actually supported the Nobel Prize winning LIGO research. So that machine learning analysis was used to rule out a supernova as being one of the causes behind the gravitational wave, anomaly. And so there is a lot of concern about how you convince yourself that your pipeline is running properly. And of course, in Silicon Valley, there's a huge community called MLOps now, where they have their own conferences. They've actually asked me to go and speak there, and I said, I'm not really a hardcore machine learning person. I'm more of a model-based AI person. So, I suggested them other people. But this is absolutely a very interesting problem, and I would say one of the tall poles in wider and wider application of machine learning in computer vision.
Awesome. I think we're slowly running out of time. Maybe a couple more. There's a lot of great questions here, and we'll find out from Jordan if there's a way to answer some of these offline. There's one from Frank. It's Licitano, if I can pronounce correctly. Any experience in using computer vision density detection that can tell us the difference between materials?
Yeah, so the density measurement, there's actually a fantastic new area of space science called gravity science. When I first heard about this, I was shocked because it sounds very science fiction-y. And so there's been a set of missions, Grace and Grail. One was at the Earth and one was at the Moon. And they fly two spacecraft over the Earth, and they know the relative positioning of the two spacecraft very well. They use laser metrology. And so when it flies over the Earth and it's more dense, it pulls the spacecraft down. And then when the second spacecraft flies over, it pulls the second spacecraft down. And this is work pioneered by Mike Watkins, who's now our JPL lab director. This is unbelievably groundbreaking work. So this actually enables us to measure the density. So like the amount of water in the California Central Valley, how dry that is and how much drought there is, or how much ice there is in the Antarctic ice sheet. The most precise measurements are from this gravity science. And so that's a way of doing this kind of gravity science and density measurement. More typically, the computer vision gives you the area or the volume. When you can combine those two, then you can get density. And so it's great how you can sort of combine all these different measurements. And that's what I would say would be one of the challenges in the future, is just combining these multimodal data sets. Just like, when I talked about the geometry with the volcanoes, you have to combine all kinds of knowledge and for our AI to be able to do that much better.
Awesome. So I think we are out of time. Steve, thank you so much. I think for everyone, thank you for tuning in. This was a wonderful presentation. And again, thank you for patiently answering all the questions. Thoroughly enjoyed the fireside chat as well. Thank you, Steve.
No problem. Thank you very much for inviting me to Jordan and to our gracious host.
Thank you.
Ciao.
Bye, everyone.